Okay, so we have a circular motion. Let's see what we have here. So we have two parts of experiment. The first part is basically you do by yourself, and then you learn some basic. So you learn. Let me check first. So we will explore the variables associated with circular motion, and so you basically you just follow their instructions. You finish, and then you don't have to write anything. Attention here. So you don't have to write anything about the first lab. You just take a screenshot of your certificate, and that'll be the first part of the lab. So we can see what we have here. Let's see. Okay, so we see, so we click on the, so what we do is just follow the instructions, click on the grid area, access simulation start page. The simulation experiment has on-screen guide instructions which you follow and complete the associated task. So basically follow their text here, follow their instructions here, and then they will like get you to do a couple experiments. Below if you look at this program. So they can be, so this one so in order to get the next round of simulation, there are 7 short sessions of this experiment. Please read fully. So basically there are 7 experiments. You finish one, then you can move to the next one. So I guess there are total 7. So after you finish, they give you will put your name in there, and then they will give you a certificate. So it has your name and your time spending on this experiment. So for the first part of this experiment, just take a screenshot of this certificate. That'll be all for the first part. Click begin to start experiment. Upon completion of all 8 iterations of this experiment, enter your first last name. So this is what I said, you enter your first and last name. The next screen shows your completion certificate. Take a screenshot of this completion certificate complete with your name and date, time of completion, and 8 rows of results. Include this screenshot in your lab report. So I just need you give me your screenshot for your certificate. That's all for this one. So we can go through like one experiment because we will not go through everything. Sometimes it's very time consuming. If you made one mistake, you have to start over, and then and until you finish, you finish the result correctly, and then you can move to next one. So this one we can begin. So the revolution per minute. So here they want you to calculate the revolution per minute. So what is revolutions per minute? So it is like the number of times of object go it tells the number of times and an object go around its circular path per minute. So it is a number. So revolutions is a number. So what kind of number? It is a number that how many rounds the object goes around in within 1 minute. Let me see. Start timer. Let's start. Okay. Can we reset? Reset here. So let's say when the ball start from here, then we start timing. Okay, then we'll wait for one, two, we just count for 1 minute. 4, right? 5, 6, 7, 8, 9, 10, 11, 12. Okay, it's 12. So then you can move to next one. I think 70. Oh, they will give you another speed to count again. And you just try to count and fill the numbers here. Then you get your certificate for the first part. So for the second part, we use this simulation lab. So we also read the on-screen informations to explore the circular motion. So we read the instructions on how to adjust simulation variable of moving or rotating mass, rotating velocity, and the radius of screen. So here, for this lab, we will look at the force necessary to hold the Hoover disk in a circular motion based on the speed of the disk, the radius of the circle, and the mass of the disk. Click on Begin button to start the lab. So you have a force here, and so you have an object. This is the force probe, which hang this one. So the weight of this one is the centripetal force. And this one is like you have a centripetal force that keeps this object to do the circular motion. Use the arrow to adjust the mass and the, okay. So we will adjust the mass and radius, generate this new speed when you want to see how speed influences tension. Then use the force probe to determine the tension in the string. Use this force probe to determine the tension in the string. So we have here the velocity is 2 pi r, which is the r is from this central to this ball. This is the r, 2 pi r over t. Let's start. So we can start from, we add 100. So, okay, click on blue down arrow at lower right on screen to reduce the mass to lowest value of 0.5 kilogram. Okay, 1.5 kilogram. Okay, kilogram. Speed randomizer stays constant or fixed for this particle simulation. So, so this one we have a random speed, but it's fixed. It's constant. Let's see. Okay. Okay, I just noticed some people are in a reading room. I like reading. They can join now. Let me see. Okay, so let me see. Okay. So set radius r to the maximum value of 2 meters. So here radius 1.5 set to 2 meters. So you see the radius is bigger. leave it fixed there for the first part of the simulation experiment. Therefore, for this first part of the simulation, you have one variable, which is the moving mass. So for the first part, we only change the mass and the two constant in the form of radius. So here we have in total 3 variables, but we keep the speed and radius constant. So we only change the mass. Click start, then thereafter start timing saying, I say when moving blue radius. Okay, let's get start. So start. Let me see. Moving blue radius line just crossed the broad dark line at 9 o'clock. 9 o'clock. 12, 3 p.m. and 6 p.m. Right? I don't know why it's like this direction. Close dot lines to make it easier to count numbers of revolutions. So basically, you can start at any point. You can start from the 9 a.m., 12 noon, 3 p.m. or 6 p.m. You can start anytime. Just make sure, like every time when, let's say you count from 9 a.m. Oh yeah. So 9 a.m. So you always count from 9 a.m. So this is what they say. And to count the numbers of revolutions in order to determine the periodic time t. See, you say 10, 20 rotation as opposed to 1 rotation to determine the periodic time. So basically, we count for 20 revolutions, and then we divide it and the time we get a number of the time, and we divide it by 20. So this is the time spent on one revolution. Click stop timer after time counting your number of rotations. Record periodic time t1 in table 1 below. So you have a table here. So let's say this is the radius. We always keep, so the first table, we keep the radius constant. So we always have the constant radius. And the speed, I guess the one you calculate speed. So this is the moving mass. You can start from, start from 1.5 or 0.5. Okay, I apologize. So we have to start from 0.5. So this is from the minimum, and then start. So you have 0.5, and then if you increase the arrow to increase the mass, you can see here. So we have the 1 periodic time. So how we calculate this one? We basically count for 20 revolutions and divided the time by 20. So we get T1. And then, someone's going. After successfully recording 2 periodic time, stop after counting the number of rotations. So after record T1 in table 1 below, do 2 times trial by clicking reset timer to set timer and get second periodic time recording for the same mass. And record this time T2 in the table. So you basically do 2 trials while you're counting your time. So you do 2 time and take the average here. And then we repeat and increase the mass. And you can, we can calculate, since we have this, the time here, the periodic time. So we can do, what we can do is we can calculate the speed, rotating speed. Rotating speed is calculated by the 2 pi r over t average. So 2 pi r is the radius, at t average, you can get from here. And this is the speed. And the force probe, force probe is you can record the data here. And then you can calculate another one, the centripetal force. So this one, centripetal force equal to mv squared over r. So you can so if you take a ohmic equal to 2 pi over t, and you can derive the, so if you take an r over r, okay, let me write down this. Text. So we have this F centripetal force equal to mv squared over r. So this is what we know. And actually, you can use this one. You can, when you calculate the centripetal force, you can use this one because the v you already calculated from here, right? So you can use mv squared over t squared, over r. Sorry, you can use this one, or you can use. So this is one way to do it. One way. The second way. Second way is a derivative. So f equal to mv squared over r, and also equal to, so v equal to 2 pi, v equal to r omega. So equal to mr, okay, mv squared, v is r omega. So we have r omega square over r, right? And the omega, what omega is 2 pi over t. So m times r squared. We take this r square out. Square omega. So omega now we can replace it by 2 pi over t. 2 pi over t. And 2 pi over t divided by r. And then we can do is, so here's the r, and here's another r. So there are two r's, so we equal to, so mr, so we cancel a lot this r, times 2 pi square over t square. So this is what we derived from here. Excuse me. Okay, so this one we will leave on the screen here. So if you check the recordings later, you can always know how we do the derivations. So that's the second way. Second way is like we have this one to calculate. So you have the two equations. Either you use mv square over r, or you use fc mr 4 pi square over t square to calculate the the centripetal force. So you list here your calculations. So they want you to do 7 different experiments. So you basically, they only list 3 of them. You list another 4. So you totally do 7 masses, different masses. Does it make sense?
Yeah, it makes sense to me.
Yes.
Yeah, I get it.
Yeah.
Okay. Thank you. Erase this. So you finish the first table. And then after you finish the first table, you will do a graph plot of the force. So the force, which is Fc, versus more moving mass. on the x-axis. So the y will be the force, x will be the mass. So you basically have 7 different data sets. You plot seven points in your graph and see what's the relationship between them. What can you infer concerning varied values of rotating masses and centripetal force? So you can see, actually, you can even tell from the equation. So Fc equals to mr, blah, blah, blah. But if you versus Fc, if you do Fc versus m, so it's like we can consider these values as a k. So that means there will be a linear relationship between Fc and m. So the slope will be r for pi squared over t squared. Let me think. Yes, this is a linear relationship. So this is what you can infer, or you can infer some other conclusions you find. For each force probe value recorded on the table 1, there is corresponding centripetal force Fc. Is there any difference in those two recorded data? So you can compare the force probe and the centripetal force. Compare the values and see if they are close or any difference, any relationship between them. What has contributed to this difference in values between force probe and centripetal force? If we find any difference between those two forces, what contribute to this difference? So basically, these two forces are supposed to be the same because this is the force probe, this hang the string, and this hanging force is a centripetal force that hold this object to rotate. So if there is any differences, that could be the measurement. So there's frictions, So when the string has contact with this board, it has frictions. Maybe it makes the centripetal forces smaller than the force probe. And is this possible for these two values to be seen? So you can tell me why they can be seen, why and why not. Just list your questions and tell me your answer. So for this lab, what we did is, so here we have 3 subsets in part 2. Remember, we have 3 variables. So first we do the mass variable and keep the other 2 constant. And then the second one, we do the radius variables. So we basically what we do is, let's stop it. So what we do, we keep the mass as 0.5 kilometer and the radius as 0.5 meter. So this is the smallest radius. And you keep this radius increasing every time by 1.5 meters. And you keep the moving mass as 1 kilometer. Okay, you can keep 1 kilometer. 1 kilometer. And then still you do the speed is constant still. So you can do 2 pi r over t average. Well, how you record the period all the time, it's still the same. So when you start, you can record for 20 revolutions and divided the time divided by 20, then you get 1 periodic time and put here. And then you do the second trial and you count for 20 revolutions and you start timing here. And then you can divide it by 20, then let's say this is for 20, or you can do time 10, you can count for 10 and divide it by 10. Put the number here and you have t average. So still record the force probe and use the equation to calculate centripetal force. You finish the second table. let's see how many data points you want to have. You have 4. So basically you have all these 4 data points. So for this lab, you don't have to write any procedures, but I really want you can show me how your calculation when you do the centripetal force and the speed. So you only show me the calculation process. No need to write any like lab procedures because it's all very clear on the lab. Okay, so I think we can check because then you plot the graph of force versus the radius, and then determine the relationship. Remember, we have this force, we have this equation. So if we do Fc versus R, so it's still m 4 pi square over t square. So all these are constant. So still we'll get a linear relationship between the centripetal force and the radius. And we get a linear relationship. Let me see, someone's asking questions here. We don't have no, we don't have to write any lab procedures for the entire lab. The first one, just show me your certificate. The second one, I think you can just list the 3 tables because we're gonna go through next table here. These 3 tables, 3 graphs, and show your calculations, how you calculate the speed and the centripetal force. That'll be fine. So what effect does changing the radius have on the centripetal force? You can tell me, so when the radius is increasing, so the centripetal force, what you can see the numbers is increasing or decreasing. So I would predict this will be increasing because it's a linear relationship. So when R increases, the Fc will be increasing. This is for the second line. And for the third one is we do the speed variations stuff here. Let me check. Okay. So we keep the radius as 1. Increase 1 radius, and the moving mass as 1 kilogram. And we do the, so we don't really know the time, the speed here. So basically we can keep one randomizer, use the speed randomizer to randomize random speed. And we can click the new speed, we have another speed. So you basically, how you get this speed, you by calculating V equal to 2 pi R over T average. So you can, the T average is you record it here, and then you start do the experiment. You save the time, you count for 20, and then divide the time by 20, and you have T1, and then you do a second time, you repeat 1 more time, and you count for 20, and the time. We count for 20, let's say when I start count for 20 and divide it by the 20, then you have T2, and take an average of this T, of 2 T's, and you have a T average. So 2 pi R, 2 pi is constant, R is constant, and you can calculate the speed here, V1, and then after you finish, record the force probe and then calculate the force centripetal force. We finish the first trial. I finish the first data point. Then you try to do 3 more. So you totally have 4. You in total have 4 data sets. And then after that, you plot a graph, Fc versus rotating speed. So you can see from here. Yeah, I think we can use this one. We use Fc equal to mv squared over r. So we can see parabola. So we can see here the relationship between FC and V is supposed to be a parallel. So I don't remember how it's called. But definitely it would be like a curve like this section. So it's like this. So it should be like this. But it depends on, you can be like this is X. Oops. So it should be like this. So this is the general graph, but you can plot in Excel and then copy paste your graph here. And then after you plot this, they ask you how changing the rotation. This is not okay. So after we do this, and they ask you how changing the rotating speed affect the centripetal force for circular motion. And you can tell based on your experiment, you can tell how they're related, and what effect does changing the rotating speed have on centripetal force. So when you increase the speed or decrease the speed, what can you tell? What the centripetal force change with? So you can list your discoveries here. So this is for the whole entire life. Any questions so far?
No, it makes sense.
Thanks. It's pretty straightforward, so not much. I think you guys can work on yourself. Like if you're got free time, you can just work the lab 5 or lab 6 and lab 6. Basically, follow the instructions very clear. And considering you guys are like have experience, more experience compared to like the new students, maybe like who just graduate from high school, they don't really know what they do. But you guys are very experienced, so I think I really trust you guys can do yourself. But it's not required. You can just finish one lab after I teach one lab, then you can finish the lab report. Yeah. So any other questions? If not, then we will take attendance and then we'll be done. Check the attendance. Okay, stop recording.